Okay, so welcome to the feedback for the chemical oceanography part of the oceanography exam for 2019. So if we just have a quick look at the mark distributions, this is just for the chemistry part of the course. I think people did very well. I mean, overall, I think the average mark was just around about 50%. So there were some students that did very, very well indeed, some not so much. So what we're going to do in this video is go through each of the questions in turn and identify kind of where people did well, where people did not so well. So I'll just put my head up here just to be I guess a record of my beard growth over the years, and also give you something to, I guess, distract you from the questions in hand. So we're going to crack on and have a look at the first two questions in this part of the exam. So there are 4 questions in total. The first 2 you have to answer. So these are the kind of the short form questions, and then there are 2 questions kind of later on when you have to choose one of them. I think most people chose to do question 3, which was about the properties of water, and very few people did the nutrients question. So we'll leave that one to the end, but we'll still go over it. So the first 2 questions, there was a question about mercury and a question about the carbonate system and CO2 and pH in seawater. So we'll just have a look first of all at, I guess, the first one. There we go, the first one. So I guess 3 parts. Why is mercury toxic? What forms does it have in the environment? And how does the form or the chemistry of mercury affect its toxicity? So you can see the mark distribution, or at least like the credit distribution. So most of the marks are for the first 2 parts, and the last part not so much. So you should have really been focusing on the first 2 parts for your answer. So the first part, what makes mercury toxic to humans? You could think about rewriting that in this kind of way. So what is it about the chemistry that makes it harmful? Now, quite a few people kind of went a little bit astray here and asked kind of answered a question along the lines of this, saying, what effect does mercury have on the body? Which is kind of, it is relevant to the question, but it is not kind of directly answering it. So it's not telling me about mercury, it's telling me about its effects, not its, the reason for its toxicity. So this is the slide from the lecture on pollution, which is kind of relevant here. So the important things are that mercury replaces selenium in kind of molecules like this selenocysteine, which forms part of kind of many kind of important larger kind of enzymes like thioredoxin reductase, this larger thingy down here. And the important thing to fully kind of get credit for this answer is not just that mercury replaces that selenium, is that when it does that replacement, it changes the function of these molecules. So it basically stops them working. And these molecules are particularly important for a whole range of things, given kind of in this kind of diagram here. So it basically stops these things happening, and that's what makes it toxic. So the next part of the question asks about what forms of mercury are present in the environment. So a few people fell over a little bit of it wasn't so much a trap, but they really misinterpreted the question, and they got really, they basically misdirected their answer, and they basically wrote an answer about where mercury is from. So, what are the sources, all this kind of stuff, which is a good thing to add to your answer once you've answered the actual question, which is about what form the mercury has. So what is its kind of, what different kind of flavors of chemistry of mercury are there in the environment? So the thing that we were really looking for here is basically a list of the different kinds of so we can have elemental mercury, so that's the kind of the either liquid mercury, which actually is very rare in the environment, even with all of the pollution that we've actually dumped liquid mercury from thermometers and chemical weapons factories and all that kind of stuff. We put liquid mercury in the ground, but actually the most common form of elemental mercury is actually mercury vapor or kind of dissolved mercury in water. We also have, I guess, more soluble. So although this guy can dissolve a little bit in water, these kind of inorganic forms of ionic mercury, mercurious and mercuric compounds, so things like, I guess, mercuric chloride is a salt which can dissolve in water very easily. This is also the form of mercury that's present in things like cinnabar. So the minerals made of mercury tend to be these ionic forms of mercury. And then we have organic forms of mercury. So we have these methyl and dimethyl mercury, which are the most toxic forms. So having this kind of basically list of things would be great. A little bit more detail would get you a little bit more marks in terms of saying that the elemental mercury tends to be the dominant form in the atmosphere. These forms are the dominant forms in aqueous environments because they're very, very soluble. And these are the kind of the forms which are, I guess, most toxic and gets taken up by organisms, produced in organisms, by organisms. Anyway. And then I guess we've already just touched on this a little bit. How does the form of mercury affect its toxicity? So, which is the most kind of bioavailable and therefore damaging, but also once it's in you, which one does the most damage? And basically, we're looking at this trend in toxicity from elemental mercury to methyl and dimethyl mercury, which are the most toxic. Okay, you could have had a little bit of description about why that is, and I guess some of you guys who are doing biological sciences went into great detail here as to why these organic forms of mercury can kind of get across kind of cell membranes because they're kind of lipid soluble. That's great. Got credit for that, which was good. Anyway, so moving on now to the second question. So this was the one about basically the carbonate system. So again, two parts. In this case, the first part worth 5 kind of marks out of 25. And the second part is where the bulk of the credit is given. So we wouldn't really expect you to spend very long kind of on the first part. And what we're really looking for here is, I guess, here's the first part written out in exactly the same way, but without the second part. You can concentrate on a bit more, a little bit. Anyway, whatever. So other than corals, so basically corals are an organism that live in the ocean that produce calcium carbonate. They do other things, and we'll get onto that in a bit. But other than that, what else is there? So hopefully you'll remember back from the chemistry of coral reefs that there are other things on coral reefs other than corals. Okay, so we're particularly looking in shallow water, tropical marine environments. So bear that in mind. So that the things that you say have to be able to live in this place. So really what the question is asking is that what organisms produce calcium carbonate? Okay. And here is kind of a collection of slides from that lecture. Now just to highlight some, we've got these coralline algae, so you can have these kind of encrusting forms, or even coralline algae that look a little bit like seaweed, like these halimeda here. We have sea urchins; they produce calcium carbonate. Fish do it a little bit in their guts. They poop out kind of microcrystalline calcium carbonate. Forams, very important in some environments. Now, I guess we'll come on to this in the next slide, but also just point out that these are the slides, and along the slides it does say which organisms produce organic matter and calcium carbonate, and it says that on kind of almost all of the slides. That doesn't mean that everything on these slides produces those things. So, for example, seagrass down here only produces organic matter. It doesn't produce calcium carbonate. A few people kind of fell over on that kind of thing a little bit, just like sea cucumbers don't tend to produce calcium carbonate. They're kind of naked, just organic matter. So I guess it says on the slides this thing, but I guess that's just because the slides were set up like that, so when I was talking about them, it would say these are things that produce organic matter and calcium carbonate. Some do both, some just do one, and so forth and such like. So I guess this follows on to a little bit of another kind of important thing that quite a lot of people missed, is that organisms that produce calcium carbonate, corals for instance, or these coralline algae, they also do other things. They don't just do calcium carbonate production. Some of them photosynthesize. All of them, if they're organisms, will do some kind of respiration. So there are other processes that these kind of things do that is not just calcium carbonate production. And I think most people missed out on that in the next part of the question. So we're looking at what is the effect on seawater, pH and CO2 of these carbonate producing organisms. So that's to say, these organisms are producing carbonate, and what is the effect of that on pH and CO2? But that's not what the question asks. It asks, what do the carbonate producing organisms do? So it's not just calcium carbonate production. They also some of them do photosynthesis. So this is a type of mollusk which has, this one happens to have symbiotic algae in it, just like a coral. So this will do some photosynthesis. It will be respiring as well. So I guess the bulk of the credit was for answering about the carbonate producing part of these organisms. But you have to consider that these organisms also do other things to the carbonate system, respiration, photosynthesis, other than just produce carbonate. So another thing that people got a little bit kind of around the wrong way is the question is basically asking, what do carbonate producing organisms do to seawater, pH and CO2? So it's basically, what is the effect of these things here on this? Now, quite a lot of you answered this question, which is, how does seawater pH affect carbonate producing organisms? Which is kind of another interesting question, but it's not the same. It's basically looking at it the other way around. So you got some credit for answering this question that wasn't asked of you, but really what we were looking for was, how do the organisms affect pH and CO2, not how does CO2 and pH affect the organisms. Although they are affected. It is a kind of a this way, that way kind of thing in reality. But the question was specifically asking about this one, so should have done this one. So I guess I've already made this point again, that what do these organisms do? It's not just produce calcium carbonate, they do other things as well. So they do photosynthesis, respiration. So so I think most people who answer this question kind of wrote mostly about carbonate production, but these things also do these other things as well. So some of the organisms, not all of the organisms, do photosynthesis. All of them do photosynthesis. All of them do respiration. Some of them, all of the ones that are carbonate producing produce carbonate. And I guess also, ultimately, these organisms will die because everybody dies. It's very sad. But the carbonate that they produce will ultimately be dissolved at some point. So that will have an effect on the water chemistry. So the kind of things we're looking for are obviously to include, you get credit for including some of these equations. So the equations for carbonate productions, that's also this one here, and you can see that takes the bicarbonate ion out of the ocean to produce calcium carbonate mineral, and that produces this CO2, and actually produces water, but that's kind of not really so important because there's lots of water in the ocean. And the effect of that is to raise the hydrogen ion concentration and lower the pH. And you could explain why that is through these series of equations down here. So if we're producing CO2, I guess the first thing to say is that carbonate production adds CO2, so that kind of answers half of this part of the question up here. But adding that CO2 does this, so it will lower the pH through producing these hydrogen ions over here. So that would have got you a bunch of marks, but it would have been better if you'd have also explained how these organisms can add and remove CO2 in other ways through photosynthesis and respiration, and how those then affect CO2 and pH as well. So I think quite a lot of people missed out on getting like the full top marks by just missing out on these additional processes. But overall, I think those that did this carbonate production, most people answer that question quite well. So good job. Here we go. Good job. There we go. Right. So those were the short questions. So we're going to move on to the longer form questions. I think most people answered this one, question 3, which was about water and its magical properties. So we'll go over that one first because most people did it, but also because it's question 3, which is next in the list of questions. So again, multi-part question. Quite a lot of people didn't write A, B, C, D. Doesn't really matter how you kind of, whether you put part A, part B. Some people even put part 1, 2, 3, and 4, even though they weren't numbered that way. That is totally fine. That does not matter. So we'll just go through each of these doobies in turn. So describe the structure of water, how the structure of water molecules leads to the formation of hydrogen bonds. So this was largely done correctly by a whole bunch of people. So what we're really looking for is, first of all, what is the structure of a water molecule? So it's kind of like 2 hydrogens and an oxygen. They're covalently bonded together. And then some description of why the molecule is polar. So I think almost everyone said that it's a polar molecule. It's got a positive end and a negative end. A few people got those the wrong way around, but that was very much in the minority. But some description about why that is, whether that description involves some mention of the electronegativity of oxygen compared to hydrogen. That draws the electrons towards the oxygen, leaving the hydrogens more positive this end, or describing these kind of lone pair electrons. That would be super great. I think almost no one mentioned that this kind of model of the atom is wrong and is not a good way of describing how electrons really are arranged around atoms and molecules. I really wouldn't expect you to draw these kind of electron probability weird orbital thingies, but at least some acknowledgement that this isn't how it really is would have been super nice. Would have got like the super top marks. This is like the difference between getting like 90% and 100%, but hee-ho, never mind. And then once you've described why the molecules are polar, it would be nice to have some, what is it that's actually attracting them together to form these hydrogen bonds? So not just saying they are attracted together, but they are attracted together by the electrostatic charges, on each end of them, kind of attracting each other. That would be super good. Again, to get that extra super top end range of the marks, it would be nice to say that they're mostly electrostatic bonds like ionic bonds, but there is some degree of small amount of covalency between molecules in hydrogen bonds. Again, some people did that to get the super top end of stuff, but not super essential to pass, for example. Okay, so moving on to the next part of the question: why do these hydrogen bonds cause water to have some of these strange properties? Now, some people wrote quite a lot about some of the other properties of water, and that was good to see that, showing some extra knowledge in that. But what we're really looking for is actually answering the specific question. So saying that it causes water to have a high boiling point, a high melting point, and a high viscosity and a large heat capacity. Those things are correct, and they're okay to put in an answer, but they don't substitute for answering the specific question. So what we're looking for in this answer here, so basically the property we're looking at is this strange behavior of water is that between 0 and 4 degrees, basically, the density kind of changes with temperature, but not in the way you would normally expect. So usually we expect water to become, or substances to become, less dense as they get warmer, and more dense as they get cooler. But between 0 and 3.89 degrees Celsius, water has this strange property that as you warm it up, it actually becomes denser, which is weird. So the question is really asking, why is that? Now, I think most people got that, but quite a few people wrote an answer about ice and water by saying, why is ice less dense than water? Which is a separate question. It's kind of related to this question. So some of the details that people wrote for that answer would have been a good thing to have in this answer, but only once you kind of answered the bit about just the water. So this is the kind of thing we're looking at. This is the property we're trying to explain, that as we cool water down from, say, a high temperature towards 4 degrees Celsius, it behaves in a kind of a normal manner. As you cool it down, it becomes denser. But then when you get to this period just before water freezes as it cools down, it goes through this kind of temperature density inversion where it gets less dense as it cools down. So that's what we're trying to explain. Now, what we're actually looking at here, or looking at for in the answer, is explaining the formation of these kind of clusters of water molecules, and that the water molecules aren't completely independent. They are kind of bonded together by hydrogen bonds within the kind of the structure of water, although they're still able to move around almost freely. So they're not bound in a crystal lattice. So quite a few people made this mistake of saying that during this cooling from 4 degrees to 0 degrees, ice crystals start to form. Now, that's not true. So they are not kind of tiny ice crystals within water. They are just clumps of water molecules that are kind of bound together by hydrogen bonds, but they're not a solid ice. So a few people made that mistake. Not a disaster, because the overall kind of gist of most of your answers was broadly correct. So the important thing is that as these water forms these clusters, they're bound together, but the clusters are bound together by hydrogen bonds, and that actually causes the molecules to be slightly further apart than they would be if the water was basically allowed to be a kind of a jumble of independent molecules. So I think those of you that got that, I think, which was the majority, that was great. What was missing in quite a lot of answers was how those clusters change with temperature. So as water cools down, these clusters get bigger, in that they're more kind of the water molecules are in clusters rather than being kind of individual little floating around little molecules on their own. So that means that more of the molecules are being held apart because more of them are in these clusters, and the clusters are larger. So that causes the density to go down as the temperature kind of goes down. Also, it would have been useful to explain why there's this density relationship over here. So as temperature increases, you might expect molecules to be moving faster, because that's what temperature is, and therefore they might be further apart as they kind of bang into each other and become ultimately less dense as temperature increases. So to explain a maximum here, really you have to explain the process that's causing density to go down with increased temperature on this side, and density to go down as temperature reduces on this side. Okay, so that would have been a good answer if you said all those things. So moving on to the next part, which was really about why seawater is different. So explain why this property of pure water is relevant or not to seawater. So what we're really looking at is this part of the graph here, and really asking, does this happen for seawater? Is this reduction in density with lower temperature a thing for seawater, or does seawater do something else? Now, quite a few people missed out on getting lots of marks in this question because they didn't answer that. They didn't address that specific property of water. They were answering questions about, does ice form from seawater at all? Or does sea ice float? About the difference in density between ice and water. Now, those are all interesting and important things, but they are not answering the specific question I was asking here. So that's the thing you should have done, focusing on, decoding the question, which I guess I tried to make a thing of during the revision session and the revision exercise, which many of you came to, which was good. Yeah, excellent. So this is kind of the theme of what we were kind of looking for in this question, in that what happens not only to the freezing point of water. As you add ions of salts, so sodium, chlorine, or any other ions to pure water, the freezing point will tend to reduce as salinity increases. That's this yellowish line on this graph here. But we're also interested in the question is asking the property of seawater, the maximum density being warmer than the freezing point. That's basically this kind of positive slope on this temperature density graph. Does that exist for seawater? So the thing we're looking for is what happens to this density maximum as you increase the salinity, and that's kind of explained by this red line, which is kind of like this red line on this graph over here, which is showing where this maximum moves as you increase the salinity. So as you increase the salinity, this maximum density decreases in the temperature in which that occurs as you increase salinity. So when you get to around 25 parts per thousand of salinity, you get to the point where this density maximum occurs at the freezing point. So when you increase the salinity beyond there, seawater will freeze before it gets to its maximum density. So it will always be denser as it cools. So this kind of anomalous kind of slope region of the temperature density graph doesn't exist for seawater. So that's basically shown in this kind of cartoon graph here, is that with seawater, as you cool down, so as you kind of like reduce the temperature on this axis, as you cool it down, it increases in density right up until the point when it freezes, and then the ice is then less dense. So saying that would be important, that seawater doesn't have a density maximum that is higher than its freezing point, would be good. Explaining why is also part of the question. So you need to say what actually is happening to the structure of water as you add these salt ions to it to kind of stop it reducing in density as it gets colder. And the thing that's happening is we're adding these salt ions and water. It's kind of like grabbing onto those salt ions, forming these hydration shells. And what that does is this charge that we're basically adding to these kind of lumps of water is actually breaking up these large clusters of water molecules, and that's then allowing the water molecules to pack together more tightly. So a few people wrote that the density is increasing because we're adding salts to it, but that's not what the property we're looking at. We're not looking at the density change due to adding salt. We're looking at the density, the change in the relationship between density and temperature, how that slope of basically this graph changes by changing salt. Okay, so by adding salt, that's what we're looking for in this question. There we go. Okay, so the last part of this question. So how does the change in density of water near its freezing point affect the formation of lake and sea ice? So again, a few people got the kind of the interpretation of the question a little bit wrong. So what we're really looking for is that this feature of fresh water. So cooling fresh water from basically 4 degrees to 0 actually makes it less dense. Okay, which is slightly weird compared to basically all other substances. So when cooling seawater, that makes it more dense, like you would expect with almost every substance. So fresh water gets less dense when it cools, between 4 and 0, whereas seawater gets more dense. So these two different kind of types of water, fresh water and salt water, behave very differently. So how do these density changes, okay, one goes up, one goes down, how does that promote or inhibit ice formation? So that's what the question is asking. Quite a lot of people wrote a variety of different kind of answers to a variety of different kind of questions, which they had somehow interpreted from the question. So one that was quite common was, why is it important that ice is less dense than water? I mean, that is a good question to ask, but it's not the question that was asked. So people were writing things about, it's important that ice floats, because if it didn't float, it would sink, which is kind of true. And if it sunk, then the surface would still be exposed to the atmosphere, and you could eventually kind of completely freeze over the oceans because they basically just pile up ice at the bottom. And, that is true. I mean, it's really good that ice floats, and, life on Earth is thankful for that, but not the question. So, so how does sea ice affect the density of seawater? So that was another kind of question that people made up. Also, it's very important for the circulation of the ocean that when sea ice forms, it ejects the salt from the ice structure, making the water more salty. That makes it denser and causes convection. Really important, but not the question that was asked. These could have been things that could have been added on to the answer to the actual question to get super extra bonus credit, but not on their own. Okay, so answer the question that was asked, otherwise bad times. So this is the kind of thing we were looking for. It would have been great to have some diagrams. People got credit for doing that. It was not entirely essential, but the point is that in the ocean, we always make the water denser when it's cooled, irrespective of what salinity is. If we cool water, it can get denser. The other thing that's important to mention is that we can only really exchange heat with the ocean. We can only warm something up or cool it down if it's at the surface. Okay, the rest of the ocean is kind of insulated from heat sources or sinks. The heat that's kind of added at the bottom of the ocean from geothermal is tiny compared to the amount that's added from the atmosphere or from solar radiation directly heating the Earth's surface. So the point is that we can only exchange heat at the surface, so this is where cooling occurs. That makes the water denser, and with seawater, it is always going to be denser. So that causes this causes the water to sink, and if water sinks down, then water from below will take its place. And this replenishing the surface with kind of water that is not frozen will mean that it's very hard to cool down the surface until it's cold enough to freeze. So this cooling induced circulation in the ocean inhibits ice formation. So ice does form in the ocean, but it will only form if you have an extremely cold atmosphere that can basically freeze the surface of the ocean before it has a chance to sink down. And it can only kind of do that once the water that's upwelling is already quite cold anyway. So it's very hard to freeze the ocean, which is fortunate if you're a fish, I guess. So the same is true of lakes, but only above 4 degrees Celsius. So you have the same situation. So above 4 degrees, when you cool the water down from maybe 10 to 5 degrees, that causes it to get denser and it will sink. And this causes convective overturning of lakes. This is a really important process because it keeps them well mixed. It allows kind of oxygen-rich water to get down to the bottom of lakes. Lake overturning occurs because water does get denser as it cools down, but only when it's warm. When lake water gets cold, and it gets below this 4 degrees Celsius, it still can lose heat to the atmosphere if the atmosphere is less than the temperature of the water. But if it cools down below 4 degrees Celsius, the water gets less dense, so it basically stays at the surface. So this forms a layer of water at the surface that can get colder and colder and colder because it gets more and more buoyant, so it gets stuck up at the top here, so it can then exchange more heat with the atmosphere. And this actually promotes ice formation because it keeps the water in contact with the atmosphere as it cools down, so it can then cool down easily to 0 degrees Celsius where it can freeze. So this is important because it basically forms a cap of cold water on top of the slightly warmer, which will be around 4 degrees Celsius. So still cold, but it will basically stop this deeper part of the lake from freezing. Now, quite a lot of people kind of got that. Quite a lot of people kind of described the ice forming a cap on the lake, which kind of keeps it insulated, which is also true. Forming the layer of ice will also insulate it from the atmosphere, keeping the lake underneath liquid. But the important thing is that it's not just the layer of ice. There's also a stratified layer of cold, buoyant water on top of, I guess, slightly warmer and bizarrely denser water below. So that's that's would have got all of the beans by kind of explaining that, which would have been great. So moving on to the last question, which very few people answered. So if you've made it this far in the video, good on you. And thanks for answering this question, because kept the marking a little bit interesting, a little bit of variety. But anyway, so this was a question about nutrients, nitrate and phosphate in the ocean. Again, many parts, 3 parts here. So describe the variability, and then questions about what are really the mechanisms for changing that variability. So we'll look at each part in turn. So the first part, describe the variability, the ratio of nutrients, nitrate and phosphate in the ocean. And the key part of this question, which was really a little bit missed by some people, was this word ratio. So what we were really not, well, I guess what we were asking is basically, how does this ratio, what is the N to P ratio, why is it constant, and where is it not constant? That's the question we were really asking. Now, what quite a few people actually wrote answers about is, how do the concentrations of nitrate and phosphate change? Now, these are, related questions, but just a question about the concentrations would have similar parts of the answer to how the ratio changes, but it's not the same answer. So a little bit of confusion arose there. But anyway, we shall go on and describe what we were actually looking for. So this is the kind of thing. So the concentration kind of changes in the ocean. Very low concentrations of nitrate and phosphate at the surface, increasing with depth. That's all great stuff to have. But what we're really looking for is, what is the, if we take this graph and divide it by this graph, what do we get? So we're looking for a kind of a description of the variability that actually there isn't much. Okay, a little bit of a trick question, bit of evil of me. But yeah, there you go. I'm an evil person. So we're looking for something along the lines of, actually the ratio of nitrate to phosphorus is actually relatively constant throughout most of the ocean basins. That you've got this ratio of 16 to 1 for every 16 nitrate atoms or nitrate molecules. There's usually 1 phosphate molecule. So that would be one part of the answer. Another thing that was really, I think most people who figured out that it was a question about ratios, answered this part quite well. And they said, "Yep, there's this Redfield ratio of uptake and remineralization of 16 to 1." But actually, the question is about variability as well. And that's a bit of a trick question, because actually there's not much variability. So if you actually look at a map, particularly in the depths of the ocean, so in deep parts of the ocean, so this is a slice of the ocean down the bottom here at about 1,000 meters, you can see that there is not much variability in the ratio. There's a little bit in some places. You might be able to see there's a little bit of a lower N to P ratio here around kind of the coast of India, maybe a bit higher in the Atlantic. But overall, we've got this ratio that's actually very close to this 16, and that's pretty much the same everywhere. So a good way of kind of answering this question is, first of all, saying, well, in the deep ocean, there's not much variability at all. Okay, that's one thing to say. And then we can actually look in the surface ocean to see actually when the concentrations are very low, okay, small changes in kind of the uptake or remineralization of one of these nutrients over the other will actually cause there to be a big change in the ratio. So in the surface, you can see that there is more variability. So that's the first two kind of scales of observations, I guess. First of all, that there's not much variability, particularly in the deep ocean, and where there is variability, it's really in the surface ocean. And then you can start to say, actually, well, where is that variability? So if we look at this map here, we can see in regions of the ocean where there's a lot of vertical mixing, lots of maybe upwelling or just lots of mixing between the surface and deep ocean. So in the Southern Ocean, in the North Atlantic, we have lots of intense mixing because it's very windy and stormy there. And places where there's lots of upwelling, so along the equator, maybe off the coast of Namibia, things like that, off the coast of Africa or West Africa here, where we're actually bringing up deep water to the surface, again, we have N to P ratios that are quite close to this 16 to 1. Okay? But if you look in the kind of the open ocean, in the gyres where the nutrient concentrations are very low, we actually tend to have low N to P ratios. And we might want to think about, well, why is that? What's going on here? Okay, why do we run out of nitrate before we run out of phosphate in these regions? Okay, so you could say things about kind of the distribution pattern, but really the first order of things we're looking for is it doesn't change much, and if it does change, it's in the surface ocean. There are some places you might just be able to make efforts. There are some places near large rivers here that you get some changes in the N to P ratio because these are very close to the sources, and we'll come on to that in the next part of the feedback arama. So anyway, moving on to the middle part of the question. So we said there might be not much variability, but if there is some variability, it's in the surface ocean. And one of the reasons for that might be the type of plankton. So live there. So this question asks a very specific question about the plankton. Why might plankton be different in terms of their nutrient characteristics? So the kind of things we're looking for here is that some plankton, although on average the uptake rate of nutrients, of nitrogen and phosphate, is around the 16 to 1. If you kind of like average together kind of a community, all plankton in the ocean, it'll be around that. But actually in particular environments, there are some phytoplankton that have kind of specialized in particular environments, and they have very different nutrient requirements. So if you're a plankton that ekes out an existence in one of these really oligotrophic kind of regions, you might have a higher demand for nitrogen than phosphorus, and that might be because you're eking out an existence, so you might have to have cells that are made up of components that are really making the most out of all of the resources available to produce energy. So they might have lots of pigments or lots of things like that, and those molecules have more nitrogen than phosphorus. You could be an organism that lives in an environment where there are lots of nutrients. So the thing that makes you competitive in the kind of the evolutionary kind of race, all that kind of stuff, is the ability to reproduce quickly. So you might have to have lots of kind of DNA and RNA type molecules to enable you to reproduce super fast. And those might be more rich in phosphorus. So you might have a lower N to P ratio. So those are the kind of things we were looking for in terms of plankton are not all the same. Why is that? So there you go. There are some slides that are relevant to that. And then the last part of the last question, moving towards the end of this feedback video, is looking at what are the processes that can actually change this N to P ratio. So the first part of the question is really, hey, what's the N to P ratio? 16 to 1. Hey, isn't it constant everywhere? Yeah, kind of. But also, it's not really. So what causes it there to be some differences? So if we go back and actually think about why is it the same everywhere? So we've got here the schematic cartoon of the phosphorus cycle and the nitrogen cycle, and the thing is that the reason why we have this near constant ratio everywhere is that most of the redistribution of nutrients in the ocean are by processes that affect both nitrogen and phosphorus, and that's really the uptake of of nutrients into biological matter, and then the decomposition or remineralization of those nutrients back into the ocean. And this recycling basically affects both nitrogen and phosphorus the same, so they have similar distribution patterns. But if we look kind of in more detail at these cycles, anything that's different between them will potentially cause there to be changes in the N to P ratio or changes in the distribution, the relative distributions of these two nutrients. So let's have a closer look at these cycles here. So what we're really looking at in terms of the recycling of these elements is we basically have an inorganic pool of nutrients, in this case phosphorus here. They get uptaken by plants, in this example taken from a terrestrial example. This could be phytoplankton uptaking nutrients. They move through kind of maybe a food web or just straight decomposition, and they get recycled back into the available nutrient pool. Round and round and round. And that's the same with the nitrogen cycle. So we get uptake of nutrients either from nitrate or ammonium, get taken up into organic matter and released back again. And they can go around this loop or they can go around this loop. But these recycling loops are basically the same in phosphorus and in nitrogen. So what we need to look at is, are there now in between these two diagrams other differences? And the key differences really are in the nitrogen cycle, we have these extra things that can happen that can't happen in the phosphorus cycle. So we have fixation, so we can take nitrogen out of the atmosphere and kind of produce useful nutrient, either nitrate or ammonia here. They can basically be made in situ, whereas the phosphorus cycle has no equivalent. Okay, the only input of phosphorus is basically from the weathering of rocks. Okay, which will also have, I mean, the nitrogen cycle doesn't have this on here, but we can also take nitrate from the land and wash it down into the ocean. Has the same source for phosphorus. The other mechanism, which is kind of different between these two diagrams, is this process of loss to the atmosphere. So taking nitrate and denitrifying it back up into the atmosphere. So the phosphorus cycle doesn't have this atmospheric loss term. The only way of removing phosphorus from the ocean is through the incorporation into biological material and sinking into sediments, which kind of also happens for the nitrogen cycle. So that's basically a loss term from this loop here, which is the same as the loss term from this loop here. So we're then really looking for, to answer this question, what processes can cause a change in the ratio? Basically, these additional kind of loops or cycles within these nutrient cycles, so basically denitrification and nitrogen fixation, when these processes happen in the ocean, they don't affect the phosphorus cycle, but they do affect the nitrogen cycle, so they can change the NP ratio. So that's kind of one part of the answer to the question. The other one is kind of basically a sneaky freebie given from the previous question, is that actually you can try to change the N-to-P ratio by changing the plankton community. So if you have lots of like bloomers, they're kind of like rapidly producing because there are loads of nutrients available, they will preferentially remove more phosphorus from the surface ocean, so they will change the N-to-P ratio that way. Likewise, if you have low primary productivity, if you have these oligotrophic nutrient-starved regions, then actually the plankton there will preferentially remove nitrate, leaving the remaining ocean more phosphorus rich. So the plankton community can have a role in changing the N-to-P ratio in the water, as well as these additional processes. And the additional processes are kind of like also kind of noted on this diagram here. So we can have nitrogen fixation, as well as this kind of effect of having kind of specialist plankton in these low nutrient areas. We can also have other plankton that come along and go, I'm going to fix nitrogen. And likewise in these regions which have got really, really high primary productivity rates because of lots of nutrients being available, as well as having this effect of having these specialist plankton that are preferentially removing phosphorus from the water, we can also have this effect of denitrification in this region where we've got a loss of nitrogen due to a lack of oxygen. So this is this idea that if you've got lots and lots of organic matter being produced in the surface of the ocean, when that falls down or when that sinks down through the water column and decays, initially oxygen is used as the electron acceptor to respire that organic material. But as you kind of use up all the oxygen, then you start to use these other electron acceptors. So we basically use up all the nitrate. So we can use nitrate to basically breathe organic matter if we're a denitrifying bacteria, and that will remove nitrogen into a phase which can escape into the atmosphere. So those were the things we were looking for in terms of questions. So hopefully this has given you a little bit more idea, firstly, about how we expect you to be able to decode the question. And it's very important that you answer the question that was written and not a question about the subject area. So I know in the revision exercise I did ask you to think a lot about what additional questions could you write about this subject area. So it was here's a past exam question, write it in your own words, and then write another question on that subject, which is a useful thing to do for revision, because that allows you to do look at topics and questions outside the limited pool of past exam questions. But that's not a good thing to do in the exam. I probably should have made that more clear in the exam revision thing. Anyway, here's a picture of giant clam. It's I think they're really fascinating, amazing, kind of cool to look at. I mean, they're really spectacularly brightly coloured, cool things when you go snorkeling on coral reefs, which you should all do before they all dissolve. So if you have more questions about the exam, then happy to talk about those. Come to the revision session, not the revision session, the exam feedback session, where we can go through your scripts, on a one-to-one, go through the questions, stuff like that. The notes I've written in them are maybe quite cryptic because they're just aids for marking. If you want to go through them, one by one, we can do that. Some of you did very well. Good job. Some of you not so much. So what can I say? Work harder. Or smarter. Work smarter, not harder. Anyway, right. Stopping now. Bye.